Okay, 2-3A. Nope. I can tell already. All right, we're going to talk about continuity. Continuity today. So, basically, a continuous function, this is the way the book says. Listen to this. It says, it's a function whose outputs vary continuously with the inputs. They do not jump from one value to another without taking on the values in between. Okay, so I think you can pretty much maybe not describe what continuity is, but have an idea or sense of what continuity is. Basically, if something is continuous, like y equals f of x, then you can draw it without lifting your pencil. So you can draw it without lifting your pencil. There we go. So what we're going to do is we're just going to look at a graph that is not continuous. And we're going to find out what the points are that are not continuous on this graph. So draw this graph as best as you can. It's going to be a weirdo piecewise function. And let's go ahead and put a dot at 1. And then an open circle down here with a line. And then, so that's 1, 2, 3, 4. And then let's start it up here and go to here with an open circle and a peak to there. And then let's put some random dot right here. Okay? Wow, it looks like a 3-year-old drew that. All right, so this is the graph of f of x. We'll just call it y equals f of x. It's a piecewise graph, has some different interesting pieces to it. And we're going to, A, find the points where f is continuous, and then B, where f is not continuous. Now, I don't really like to ask the first part, but the book does. We want to find the points of continuity. I usually ask, what are the points of discontinuity? But let's do them both, just so you know how to do both. So we're going to list the points of continuity. When you do this, you're just doing the intervals of x. Okay. So the points of continuity would be from 0 to 1. So it's continuous from 0 to 1. And then it's continuous from 1 to 2. These are intervals of x. And then it's continuous from 2 to 4. And I don't know if the brackets and the parentheses are bothering you. Yeah. Brackets mean it is included. Okay, so this point right here at x equals 0 is part of my interval, but 1 is not because 1 was an open circle of this interval. But then 1 is included here, but 2 was not. 2 is an open circle. It's not continuous at 2. And then it is continuous from 2 all the way to 4, including 4 because 4 has a solid dot at it. Now, the question that I rather would ask would be, what are the points of discontinuity? Discontinuity. Sound it out, spell it right. There you go. What are the points of discontinuity? Now you can see them. It's where you had to lift your pencil in order to graph. So, for example, I'm walking on my graph and I'm continuous right here until I get to x equals 1. And then I'm continuous on my graph and I have to lift up my pencil also at 2. X equals 2. But then I'm continuous for the rest of the graph. So the only points of discontinuity would be at 1 and 2 for x. Yep. The open circles, the jumps. We're going to talk about what type they are in just a minute. All right, so here's what you need to know about continuity. Continuity at a point. Continuity at a point. And I know C is not a point, but this is the way they say it. Continuity at a point C. Hi. in order to be continuous, 3 things must happen. Jihoon. Ooh, you got a bad slip. There you go. Yes, get that cleared up. All right, 3 things need to happen. Number 1. First of all, the function must exist. The function must exist at x equals c. Okay, there has to be a point there. There can't be no value. So we can say that f of c equals some value b. We don't know what it is. It could be 1, it could be 3, it could be negative 1,000, whatever. But it exists and it has a y value. Okay? So that's the first thing that's true. And that makes sense, right? If I'm going to be continuous at x equals c, there must be a point y, or, part y of it. Okay, number 2. The second thing that happens is the limit as x goes to c of f of x exists. I don't know what that is either. It could be 5, it could be 10, but the limit exists there. It has to, okay? So to be continuous at any point, and you come in from the left, you come in from the right, the limit has to exist at that point in order to be continuous. And then, here's the last one, which is the most critical, is that the limit as x approaches c for f of x has to equal whatever the value is there. Has to equal that b that we did there, okay? So the limit has to exist, and then it also has to equal the same value of y. All right, so let's move on to finding our 4 types of discontinuity. So here we go. There are 4 types where these things fail. In Ham, I don't know about RAM, but I know in Ham we learned 3, and we're going to learn 4. Yes, one is a jump. I'm sure RAM did it too. No? No, not limits, but discontinuity of functions. No? No. Oh, okay. Yeah? All right, the first one that happens is called removable. People like to call this a hole in the graph, which is true. They took a point and they removed it from the graph, okay? They didn't make the graph jump anyway or go to infinity. They just took out a number. You're walking along the graph and all of a sudden they just took a piece out, okay? So for example, something like this. F of x equals x squared minus 25 over x minus 5. Okay. Now when you look at that, it looks like there's going to be a vertical asymptote there. That's what everyone thinks, right? Except once you take this and factor the numerator. What happened? You were just talking to yourself? Oh, that's allowed, especially in mathematics. All right. What happens is it's a hole in the graph. Okay, it's not an asymptote. It's a hole in the graph. And when you go to graph this thing, it looks like a line. It looks like the graph of y equals x plus 5. Y equals x plus 5. Okay, it's not quite that graph though. If I go to 1, 2, 3, 4, 5, and I draw a line, at positive 5, there's not a value there. At x equals 5, there's a hole in the graph, but it keeps continuing on. Yep. Okay, so let's see. Right. We're graphing the original. We're graphing this graph right here. And that graph, the domain is all reals except for x is 5. But when I go ahead and simplify my function to graph it, it looks just like a line, but I have to remember that 5 doesn't work for my original. Okay, so what does this fail out of those 3 things that we just talked about? It says the function must exist at x equals c. Well, guess what? At 5, the function does not exist there. Okay? It fails that one. It doesn't fail number 2, though. the limit as x approaches 5, the limit is whatever that y value is, which is 10. The limit, write that down, because a lot of people think that the limit doesn't exist at 5. But if you remember, the limit is not what y is, it's what it's approaching, right? And so the limit is 10. And then 3 says the limit has to equal whatever the value is. Well, there is no value there. So it fails that first one, and then it actually fails the third one too. What are they what?
Like these 3 things.
Like what are they in the book?
Yeah. Like, what is it failing to? Like,
Oh, continuity. Yep, it fails continuity. Okay, so that's our first one.
Why is the limit 10?
Oh, the limit's 10 because if you solve the limit of this algebraically, you would do the limit as x approaches 5 for x squared minus 25 over x minus 5. And then what we did is we factored it, and you get x plus 5. And then you take 5 and plug it in, and you get 10. If you look at it graphically, no, it's not the stylus, it's the app. I need a new app. I'm going to look for a new app. Yeah, they did an update last Friday, and it screwed everything up. Callie came up to me, she's like, are you having troubles with... I know.
We can just show you.
Yeah, okay. After this, okay. So, but if you look at the graph, you're going towards 5 from the left, and you're going towards 5 from the right. They're approaching the same y value, which happens to be 10. It doesn't equal 10, but that's not what a limit is. A limit is as I'm getting closer and closer to this x that I want, what's my y getting closer and closer to, and that would be 10. Okay, let's move on. Number 2. The second out of the 4 is called a jump discontinuity. Okay, this is not removable. It's a jump in the graph. You're going along, and all of a sudden you have to jump up to get to the next part. I didn't have to jump. I didn't kind of jump over the hole, or like, you know.
With the graph of, what is it called, the I?
Yes, that's what I was just going to do. The greatest integer function, intx, the one that we've been graphing on our calculator. That is a great example of a jump discontinuity, because this one goes like this. It goes here, and then at 1, it jumps up to 1. And then it keeps going, and then at 2, it jumps up to 2. See how different that is? And a lot of people get the removable and the jumps mixed up, but the graph's not connected here, okay? So this one actually is not continuous at all of the integers. This fails the discontinuity at the integers. And it actually fails, not the first one. Like if I was going to take the limit as x approaches 1. For this function, we'll call it f of x. If I took the limit as x approaches 1, I would go this way towards 1, and I would go this way towards 1. And they don't equal each other. So the limit does not exist. Well, to be continuous, you have to have a point, which we do. At 1, there is a value. F of 1 equals 1. Okay, so it doesn't fail the first one, it fails the second one, which says there has to be a limit there. There is no limit. All right, let's move on. Number 3, the third one.
Does it fail the third one?
Yeah, it fails the third one too. Because it has to be equal, and if there's no limit. Yeah. All right, this one is called, we don't see this one that often. It's oscillating. Oscillating discontinuity. Okay. We haven't seen this yet this year, I don't think. A really good example that they use all the time would be f of x equals the sine of 1 over x. Okay. As you can see here, the domain would be all reals except x is 0. Okay. And when you go to graph this, I'll graph it for you, the sine of 1 divided by x. If I go to graph this, it does some crazy stuff there at 0. And let's even zoom in on it. Weird, huh? Okay, what's happening is your graph, it's going along. It's going like down here, and then it goes like that. Okay, I don't even know what it does on the outside. But as x approaches 0, This is not continuous there because the limit doesn't exist. It just keeps bouncing back and forth between numbers. It never zeroes in on anything. And so that's called oscillating. That one's the one that we'll probably do the least. Okay, and then finally, number 4 is the one that you've been doing the most lately, and this is infinite. Infinite discontinuity is when you have a vertical asymptote. Okay, these show up vertical asymptotes. So let me just give you a very basic. F of x equals 1 over x. Okay, that's just one of those rational functions. Looks like this, here and there. And so we know that there is a point of discontinuity at x equals 0, because x equals 0 is not in the domain of our function. So at x equals 0, it's an infinite discontinuity because it goes to positive or negative infinity. So there is no value. F of 0 does not exist. Okay? The limit of f of 0, the limit as x goes to 0, sorry, it says limit, does not exist either. Because on one side it goes to infinity, on the other side it goes to negative infinity. All right, so we're going to do a couple here, and then we'll be done. All right? So, number 2. Number 2. All right. Y equals 1 over x squared minus 36. 1 over x squared minus 36. We are going to find the points of discontinuity and what type they are. Find the points of discontinuity. Okay, find the points where the graph's doing some weird stuff. And the type of discontinuity that it is. All right, a lot of times you can tell just by looking at the graph. Okay? You can graph it on your calculator, that'd be great, but sometimes you're not allowed to have your calculator. So let's kind of do it both ways. So let's do this. We know that this is the graph of, and if we were to factor the denominator, we would get x plus 6 and x minus 6. So I know that my domain is not all real numbers. Something weird or bad is happening at x equals 6 and at x equals negative 6. Now, neither one of those are a hole in the graph because there's not the same factor up top. So it actually fails in the same way, and that would be what? Does anyone know? Which type? Well, they're vertical asymptotes is what they are. Infinite. This would be failing, and the type of discontinuity would be infinite. And you can try and graph that on your calculator, but you'll see at 6 and negative 6, there are vertical asymptotes. When vertical asymptotes, that means that it goes to infinity. All right, let's try one more. Number 3. X squared, or y equals, let's do y equals. That looks really bad. Y equals x squared minus x minus 6 over x squared minus 3x. Okay. So let's find points of discontinuity here. Well, the points, yes, we're going to have to factor a lot. Points of discontinuity are going to happen at the zeros, anything that we can't have in our domain. So let's factor the numerator. And this would be x minus 3, x plus 2. And then let's factor the denominator, which would be x, factor an x out. You're left with x minus 3. Okay. So we can tell right now our points of discontinuity are going to be the points that are not in the domain. So at x equals 0 and x equals 3. Okay, those are not in the domain, so there's no y value for them, which means they're not continuous there. Now, as you noticed, I gave you one that had the same factor. Yes, So at x equals 3, this is a removable.
So whenever anything can reduce.
Mhm. Yep, exactly. It's a hole in the graph. And then x equals 0, it doesn't reduce, so it's going to be a vertical asymptote, so that would be infinite.
Oh, there's two.
Yep, there's 2 this time. Well, there's 2 last time, but they were different. They acted differently. One was infinite and one was removable.